Good day, everybody. It's a pleasure for me to speak at the first online conference on nonlinear dynamics and complexity, and I would like to thank the organizer for putting together such a beautiful event. I just regret not being in person with you due to the circumstances that we are all living, unfortunately, in these days. The subject of my talk is about the setting of collective states in networked phase oscillators, and in particular, the setting of explosive synchronization and this new state, the Bellerophon states. These are results we obtained in the last few years within what is now called the Stefanos Nadir, that is an international research team on networks and data science, which includes several collaborators all around the world, some of them from Spain, as you will see here, and some other from China. Synchronization is a very old problem in physics, and already in the 17th century, Christian Huygens discovered that when you have two pendula hanging at the same wooden beam, they start to develop a collective state, which he called sympathy, not synchronization. He called it sympathy. That is a state in which the clock starts to work in antiphase. And Huygens understood very well the reasons why this state was set up in the system was just because the clock were coupled by tiny forces that they interchanged through the common wooden beam. So he understood very well that tiny coupling can produce macroscopic collective phenomena. These phenomena are studied in different kind of models and systems, and I would like here now to spend a few minutes to describe the Kuramoto model. Many of you certainly know, but just to figure out the fundamental details, just for having in mind what we will then use in the rest of the talk. So the Kuramoto model, in the original Kuramoto model, what you have is an ensemble of phase oscillators. Each one is characterized by the given frequency omega n. That is, in absence of any interactions, each oscillator has a phase theta n, and the derivative in time of this phase is the frequency omega n. So each oscillator, in absence of any coupling, is just a point which is rotating or counter-rotating depending on the sign of such a frequency omega. We are interested in the setting of collective phenomena. So what we take an ensemble of a very large number of such oscillators, each one having a different frequency. And we suppose that these frequencies are randomly picked from an usually known distribution G omega. This distribution G omega is extremely important because it will constitute the first ingredient of the recipe that we are going to describe. So please keep in mind the frequency distribution G omega. Then when you have to couple this, and the Kuramoto model suggests to couple them in a sinusoidal all-to-all coupling form, that is by means of a coupling strength D, and the sum over all the oscillator of the sinus of the phase difference. When D is large, if D is large enough, what you observe is that all these oscillators, which initially start in a configuration which is filling up entirely the curve, the unit circle, actually group together and form a single cluster, a single synchronized cluster. In order to measure this transition, because the main point is how to describe the transition between these two phases, full incoherence, where all the oscillators are having different phases and different frequencies, and full coherence, well, they all have same phase and same frequency. We refer usually to the Kuramoto order parameter, which is nothing but considering the associated vectors to each one of the points of the phase oscillators, this e to the I theta, summing all of them as vectorial sum, taking the modulus and divided by the number of oscillators. So you understand very well that if we are in the coherent state, all these oscillators are grouped, the sum is done coherently in the direction of the vector. So this quantity is of the order of n, and r is eventually of the order of 1. If we are instead in the situation in which we have incoherence, then all these oscillators are distributed on the unit circle, and they pairwise tend to annihilate, so eventually R is very similar to 0. Therefore, we have a path to synchrony in this model. As we increase the coupling strength D and we monitor the order parameter R, we pass from the incoherent phase, where all oscillators again are filling the circle, to the fully coherent state, which is the synchronized state. And the rest of my talk will concentrate in this middle situation, because we want to describe the transition path from incoherence to coherence. There is a slight change in what I'm going to say, because we are not investigating this problem in all-to-all connected systems, but in networks. And the reason is that synchronization in network is very important in many applications, from brain to power grid, from the internet to neurons. And in order to do so, we simply need to take the model, the Kuramoto model, and plug here the adjacency matrix of the network. So this matrix A and M is the adjacency matrix. Is a matrix of zeros and ones. 0 if there is no link between oscillator N and oscillator M. 1 if there is a link between oscillator N and oscillator M. And this is the second ingredient of our recipe. So what we are going to see now is that combining properly structure of the network and dynamics of the oscillators, one can obtain different kind of transitions and different kind of collectives. Now, just again as a small introduction, in physics, when the system changes from one phase to another, like, for example, in magnetization or nematic state of crystal, you have indeed the control parameter and order parameter, and you have a transition between these two phases. And there are basically two important classes. One is the class of reversible processes and continuous, where the phase 1 and phase 2, so you start from phase 1, you increase gradually the control parameter, and you have a continuous transition to phase 2. And this transition is fully reversible in the sense, if you start from phase 2 and you decrease the control parameter, you obtain exactly the same transition curve. And instead, as opposed to this, you have the first order like phase transition, in which you have the system passes abruptly from phase 1 to phase 2. And usually this is a process which is not reversible, in the sense that starting from phase 2 and decreasing the control parameter, you may eventually end up falling down in phase 1, but for a different value of the critical parameter. So you have an hysteresis, you have an hysteretic process that marks clearly non-reversibility of this. Let's go ahead. Okay, so in the classical Kuramoto model, the transition is second order like, that is continuous and reversible. And some recent studies have shown that it's possible to have this transition to be first order like, for very specific arrangements. For example, very specific arrangement in the frequency distribution. When the frequency distribution is equispaced, so I take frequency of this point, I give 1 W, then W plus delta, plus 2 delta, plus 3 delta, and so on and so forth, I can have first order transition. Moreover, I can have first order transition also when I have a sort of proportionality between the frequencies, omega I, and the degree distribution of the network, Ki. So I have nodes which are now connected to a different number of other nodes. Ki is the number of nodes to which node I is connected. And so if I pre-impose a sort of proportionality between the frequency of the node I and the number of connections that this node I has with the rest of the network, I can obtain such abrupt transitions. So we started from this situation, which these initial studies have pointed out that there is possibility of having a first-order transition for very, very specific cases. And instead, to demonstrate that this transition is very generic. And so let us skip for one moment because we don't have time to show up this, but this is a beautiful experiment that was realized in Madrid, in which showed that indeed such specific first order transition can appear in experiments. So the system can also pass from a transition which is continuous to a transition which is discontinuous. But let us then discuss the problem of generality of first order like transition. And I told you that the first ingredient is the frequency distribution, the second ingredient is the structure of the network. So the first step we wanted to do is let us now fix the frequency distribution, and let us now demonstrate that for whatever frequency distribution we fix, there is always at least one network configuration which renders the transition explosive. So what we do is we take our nodes, our ensemble. We said we fixed the frequency distribution, so we already assign the frequencies to the different oscillators. And then we pick a random pair of oscillators, ij. And then we check the frequency difference between these two oscillators. And if the frequency difference is larger than a given threshold gamma, then we put a connection. Otherwise, we don't put a connection. And we take another pair. And then we continue pairing and pairing and pairing and pairing up to obtaining a final network which has a given number of connections, that is, which has an average degree. We use this network here as adjacency matrix, and look what happened. If in our algorithm gamma is 0, that is, we don't put any constraint, then what we do is a simple random network. And as it is the classical case, I expect to have a very continuous phase order transition and reversible. But then when we increase gamma, you see, for example, that at a given time, gamma equals 0.4, you obtain a first order like transition, that is an abrupt transition here, from the incoherent to the coherent phase, and a backward transition which goes down to incoherence for a different value. So you get hysteresis over here. Actually, what you can do, you can calculate exactly the dependence between the frequencies and the degree, because since you have forbidden for each node to form links within a specific frequency area, you can calculate the expectation value of each degree. And you obtain that in the presence of, when the system sets up this explosive synchronization feature, you have associated the appearance of a specific V-shape emergent correlation between degree of the node and frequency of the node. And this is valid, you see, for a symmetric distribution as well as for an asymmetric distribution. And actually the same happens. You have the settings of such first order like transition together with the emergence of specific correlation features between Ki and omega I. The same happens for weaker rules, which means instead of having a threshold in the difference between the phase, the frequencies, we can have a threshold in the difference between the frequency of node I and the average of frequency of the neighborhood of node J, or vice versa. And in all cases, you get the passage from a continuous reversible transition, which is the black line here for gamma equal to 0, to a discontinuous irreversible transition, which is the blue line. This is very, very important, because if I go back, this means that I am imposing a barrier in the connection, so that in my network there is never a pair of connected oscillators which are close by in frequencies. So this is very important. I put a frustration mechanism in the formation and initial formation of synchronization, which frees the system in the coherent state up to the moment in which the system jump altogether to coherence. The second step is, okay, so we have demonstrated that if you give me the frequency distribution, the first ingredients, I give you the second ingredient. But now let's do even more general. So now you choose both ingredients. You choose the frequency distribution, and you also choose the network. So I have here a network of oscillators in which the frequencies of oscillators are fixed, and also the connections are fixed. So the only thing I can do in this condition is I can weight, so I can make thinner or thicker connections. And the idea is very simple. I will put here a weight omega ij alpha, which is a power alpha of the absolute value of the frequency difference. So once again, if two oscillators have very close frequency difference, when alpha is positive, this weight is small. When the oscillators have very far away frequency difference, this weight is large. So it's again very similar to the previous case. When you do so, you obtain something which is really remarkable. That is, if you put alpha equal to 0, that is, you don't weight, because for whatever is the frequency difference to the power alpha, you get always 1, so you have an unweighted situation. You have the normal case, so the second order like transition, continuous and reversible. But if you now put alpha equal to 1, you have a very important result. It's no matter which is the frequency distribution, you have an universal first order like transition, which only depends on the structure of the network, therefore, not on the frequency distribution, in which the system is frozen up to this point in which it goes up suddenly in the forward transition, whereas in the backward transition, it starts from coherence and goes back down to incoherence at different values with hysteresis. And this is, as you see, exactly the same curve for uniform distribution of frequency, for Gaussian distribution of frequencies, from bimodal, Rayleigh distribution, semi-Gaussian, whatever distribution you consider here. So you have a sort of universal distribution. Once again, you have the appearance and emergence of a V-shaped structure of correlations, this time between the strength of the oscillator, so the sum of all the weights, not the degree, and the frequencies, omega I. And moreover, you can do something even better. That is, you can, starting from this first, you put alpha equal to 1 here, so starting from this first weighting, you can put a second weighting to the link between us. So you can use another important characteristic, which is the number of shortest paths that are formed through that specific link to power beta. And if you do so, you have the possibility of modulating the irreversibility of this first order like transition. That is, you can make the hysteresis larger or smaller, so you can take this universal first order like transition and change the hysteresis properties as you wish, basically. Okay, so there are many other ways to make this first order like transition. Are very general, but I have no time, because I'm last with the last. I have only another 10 minutes, and I need to cover the other part of the talk, which is the Bellerophon state. The important point is the following. It's in the first order light transition, the system is frozen, so there is no cluster of synchronization. Whereas in the second order light transition, there are cluster of synchronization which grows and merge up to have a giant cluster eventually. So the idea is now I hope to have convinced you that you can prepare the systems somewhere in a rather general way to observe the two transitions. For instance, let us consider the Kuramoto model in which we take two ingredients. One is we dishomogeneously couple all of our oscillator to the mean field. That is, this Ki is a given K, a given coupling strength, times the absolute value of omega. So fast oscillators are more coupled and slow oscillators are less coupled to the mean field. And moreover, let us take a bimodal Lorentzian frequency distribution, which is g omega given by this formula. So you have a two peak distribution, one peak at plus omega 0, another peak at minus omega 0, and the width of these two peaks of the distribution is delta. So you see delta is the width parameter, plus and minus omega 0 are the Celtran frequencies. And now you play a little bit and you see that depending on the value of omega 0 divided by delta, the phase transition can be first order or second order. You see, for these particular values, you have first order, then the hysteresis shrinks more and more, and eventually you get to a second order. So in these conditions, you don't have intermediate clusters of synchronization. In this condition, you do have intermediate cluster of synchronization. And now the question is, if I put myself exactly in the tri-critical point, that is, in the point in which the transition passed from being first order to being second order, should I see clusters in the middle or not? If I stay epsilon to the right, I see clusters because the transition is continuous. If I stay epsilon to the left, I don't see cluster because the transition is discontinuous. What happens when I am exactly in the middle? When I am exactly in the middle, first of all, the system is solvable, so we solved it completely, so we can find exactly the value of this tri-critical point, because we can have a solution for the critical point of K for forward and backward transition. The backward transition is independent on omega 0 divided by delta. The forward transition depends, so the intersection is exactly square root of 3, and it's the point where we put ourselves, the tri-critical point. What happens? Now I am here showing three plots, three snapshots. In this snapshot, I'm showing the phases of the oscillators. In this other snapshot, I am showing the instantaneous frequencies of the phases. And here, I'm showing the long time average of the instantaneous frequencies. So when I put myself in the tri-critical place, these states suddenly appear. These are particular states, and they are very, very particular and different from all the other states that have been seen so far. So if I put myself there and increase the coupling strength, I see no coherence, so the phases are not locked, frequency not locked, and therefore also no locking in the average frequency. Eventually, when I have full coherence, I have completely equal identical frequencies, completely equal average frequencies, completely equal phases. In the middle, I have the formation of cluster in the average frequency. That is, this cluster corresponds, as we will see, to a quantized value of this long time average frequency. This value is +1. This is 3 times, 5 times, 7 times, 9 times a fundamental frequency. So this, in average, have the same frequencies, but instantaneously they don't have the same frequency. So they are not locked in frequency because if I see now the oscillators belonging, for example, to this cluster, they have this distribution of instantaneous frequencies. They are not locked in frequencies, and they are not locked in phase. The phase goes from -p to +p. So I have the formational clusters where elements of this cluster are neither phase locked nor frequency locked, but they are locked only in the terms of the long time average frequencies. This can happen only if the instantaneous frequencies are periodic, and therefore they have a sort of periodic behavior, rhythmic behavior in the instantaneous frequencies. So they behave periodically in time in the way that their average value are the same. So they have at the given time, if I make a snapshot, this let's say this characteristic. Another time they will have this other characteristic. So when they sum up over the period, you get a flat here. So this corresponds, unfortunately the movie doesn't work, correspond a very complicated motion for all the elements of each cluster. So if I take here, the elements of the different cluster, I see very, very complicated motion because their phases are not locked. And I have a mutual periodic motion. I cannot show you the movie, but what I can do is I can take all the elements of cluster 1, cluster 3, cluster 5, and restrict myself to the calculation of the Kuramoto order parameter only to these elements. So the Kuramoto order parameter is indeed a complex number, so I can report the real part of this against the imaginary part of this, and I have a rhythmic state, and I have a limit cycle of order 1. In the same period, the elements forming cluster 3 are forming period 3 cycle. In the same period, the elements forming cluster 5 are forming period 5 orbit. So each of these cluster corresponds to a global rhythmic state, global in the sense of the Kuramoto oscillator, which is quantized in frequencies in the sense that the average speed of these coherent clusters corresponds to odd numbered multiple of a principal frequency. And this is completely new in the sense, this is not this is an asymptotic state of the system, but it's not stationary. And it's an asymptotic state of the system is a collective asymptotic state, but is not corresponding to a phase-locked or a frequency-locked state. Then the question is, are Bellerophon phase generic? Because I demonstrated them to occur in a critical point, which is a very, very specific point. We have demonstrated, in fact, it is easy to extend this to two populations of oscillators. So imagine that instead of having Ki, you have two populations of oscillators. And let us take the framework of Steve Strogatz, in which the population of oscillators are a population called conformists, which have a positive Ki, so they link to the mean field positively, and the contrarians have negative Ki. Well, it is well known that if I have a population which is only formed by contrarians, then the emergent dynamic cannot be other than incoherent. However, when a portion of such contrarians are flipped into conformists, there is the appearance of synchronization. And again, oscillator from contrarians to conformists can be done randomly or according to the absolute value of the natural frequencies, or starting from the largest to the smallest, or the opposite, starting from the smaller to the larger. I have only 2-3 minutes left just to tell you that this is exactly the case these Bellerophon states are exactly the same, with the same characteristic that the one observed in the three critical point, and then you can mix the two situations. That is, you can consider heterogeneity together with conformist and contrarian, and you can have hybrid states in which you have the superposition of odd numbered and even numbered Bellerophon states with very, very complicated structure of periodic orbit and even non-periodic orbit in the global rhythm of each cluster. I have not sufficient time to discuss all of these cases, so I use the last couple of minutes is to show you up a series of literature you can read if you are interested in the presentation. I told you this is a presentation including many, many results that you obtained over the year. If you are in general interested in synchronization, there are two, so to say, rather, I can suggest, one monography we wrote in 2002 and a recent book that we wrote for Cambridge University Press. If you are interested in network dynamical systems, I suggest two physics reports, very large physics report, one on 2006 and one on 2014, in which we discussed very deeply the structure and dynamical part of monolayer networks and multi-layer networks. If you are interested in explosive synchronization, here is the fundamental reference of the last years. And we also wrote a large monography in which we summarize the main results regarding various explosive transitions that were seen in complex network structure and dynamics, not only in synchronization, but also in percolation. And finally, if you are interested in Bellerophon state, the last part of the talk, this is the relevant literature in which we describe the state. We generalize to the case of contrarians and conformists. We give the exact conditions for the Bellerophon states to be observed, and so on and so forth. And last but not least, I thank you for your patience. I'm very happy to answer whatever question you would have. And I allow myself to make a little bit of publicity to Chaos, Oscillators, and Fractals. Is a journal by Elsevier, of which I'm editor-in-chief. And, this journal, with a lot of effort from the side of the editorial staff, succeeded to grow a lot in the last years. And now in the last years, we got a very nice impact factor, an impact factor here you see of 3.764, which make now this journal the most prestigious and important venue in the world for statistical and nonlinear physics. Here there are two mistakes. It's not word, but it's word. And this is no linear, but it's non-linear. But in any case, the venue is really growing again. We have a very big visibility, and I invite you to submit your best paper to us. Maximum 5 per year per author is the only journal in the world which has this policy. We only publish a maximum of 5 papers per author in a year. And we count the number of papers which were published by each author, so we want to really have, really cover, and really give the opportunity to everybody to contribute to us. Many thanks, and I'm open to answer your question. Thank you. Thanks again.